Hello, my name is Hany Assasa and I'm a senior system engineer at Pharrowtech. In the MARSAL project, I lead task 3.2 and the goal of this task is to design and develop a hybrid mmWave MIMO Fronthaul for a cell-free radio access network in the ORAN architecture. The cell-free network requires fronthaul links with a high capacity and low latency to facilitate real-time coordination between the radio units RUs and the distributed unit DU. In this video, we demonstrate the two demos that we have built as part of the proof of concept 1.1 in the MARSAL project. We start with our first demo to show our real-time 60 GHz SISO Fronthaul solution. Our solution integrates Pharrowtech's 60 GHz CMOS-based RFIC and phase antenna array module with Renesas RWM6050 mmWave baseband wireless modem. The system is IEEE 802.11ad standard compliant and implements all the necessary MAC and PHY features mandated by the standard. This includes automatic beamforming training, automatic gain control, rate adaptation, and various channel access periods. The system supports point-to-point and point-to-multipoint communication in TDMA fashion. Our system can achieve a throughput of 3.5 gigabit per second using MCS12, which is the highest modulation and coding scheme supported by the IEEE 802.11ad 2012 version that uses 16 QAM with an LDBC code rate of 3/4. So our demo consists of two 60 GHz kits. One of the kits acts as a PCB or access point. The other kit acts as a client or CPE. The PCB transmits directional beacon frames to announce its existence in the network. And the CPE, on the other hand, scans all the channels searching for the PCB. Once the CPE finds the corresponding PCB, it performs beamforming training, followed by association to establish a directional communication link. Now we start an IPERF3 session in the downlink direction from the PCB to the CPE. On the CPE, we monitor the reported throughput. As you can observe, our system is capable of achieving 3.5 gigabit per second over the air, which is extremely high throughput. Now we move to our second demo, which shows our prototype of a hybrid mmWave MIMO Fronthaul. In our previous demo, we achieved 3.5 gigabit per second. However, to increase our throughput, we need to utilize MIMO technology. MIMO technology allows transmitting and receiving multiple data streams at the same time and same frequency. At the moment, no commercial 60 GHz baseband modem that supports MIMO communication. As a result, we had to prototype the system using AMD Zynq UltraScale Plus RFSoC technology. The RFSoC technology is a complete system-on-chip SoC for single-chip radios that includes a full ARM processing subsystem, including application processor and real-time processor, programmable FPGA fabric, RF analog data converters, and soft decision forward error correction cores. Our demo consists of two RFSoC kits, where one acts as a transmitter and the other kit here acts as a receiver. We connect two analog RF front ends per RFSoC. Our prototype is capable of transmitting and receiving two spatial data streams simultaneously. We use an external reference clock to synchronize all the analog RF front ends on the same side. This ensures phase coherence, transmission and reception, which is essential for MIMO communication. To prototype this system, we performed the following steps. We designed and fabricated a breakout board to interface our RF evaluation board with the RFSoC ZCU111 kit. For the second step, fabricated mechanical brackets to hold the RF evaluation board together with the RF breakout board. Finally, we implemented all the required software and hardware components to facilitate the control of the analog RF front ends by the RFSoC kit. For the hardware design, we have implemented all the necessary IP blocks on the FPGA to inject and retrieve IQ samples from the RF data converters. We didn't build any hardware accelerators, but rather we do all the signal processing offline in MATLAB. For the software architecture, we have developed the following components. First, we built a comprehensive framework in MATLAB to control all the RF front ends and communicate with each RFSoC kit. The framework follows an object-oriented programming paradigm and allows configuring the system in various communication modes. This includes SISO, MISO, CMO, and MIMO. The second component is a MIMO application, which runs on the application processing unit and integrates the C library to control each RF front end independently. For the FPGA design, we follow a memory-based implementation, where we generate the waveform offline using MATLAB and then feed it to the FPGA. The FPGA stores the IQ samples of the waveform and transmits them constantly in a loopback mode. We start with a baseline demo using SISO communication mode to validate our implementation. We utilize the open source implementation of the IEEE 802.11ay standard developed by the National Institute of Standards and Technology NIST. The IEEE 802.11ay standard is an enhancement of the IEEE 802.11ad and supports MIMO communication in single-user and multi-user modes. We demonstrate here a SISO link on the RFSoC kit, in which we have generated an IEEE 802.11ay frame, modulated and encoded using MCS16, and injected into the FPGA. The size of the frame is 4 kilobytes and uses a normal size guard interval. On the receiver side, we regularly capture the IQ trace and pass it to our signal processing chain in MATLAB, which performs the following set of operations. First, it detects a waveform in the trace, then it passes the detected waveform to a root race cosine filter. Third, we perform coarse and fine carrier frequency offset and symbol timing offset estimation. Fourth, we estimate noise variance and signal-to-noise ratio from the preamble. Fifth, we extract channel impulse response and channel frequency response from the channel estimation field. Sixth, we equalize the payload and track phase changes. And the final step, we decode the payload and report the decoding results, including bit error rate, error vector magnitude, and signal-to-noise ratio. Now we move to the MIMO communication part. Here we generate two spatial data streams and boost them to the FPGA loopback memories, where each loopback memory is connected to an analog RF front end. Then, we release the output of the two memories to ensure synchronous transmission. On the receiver side, we capture a set of IQ samples synchronously, and then push these two streams to MATLAB for post-processing. The MIMO communication is divided into two phases. In the first phase, we do channel sounding. Here, we transmit two data streams using a set of transmit and receive analog beam patterns. Each data stream contains a unique preamble for stream identification and synchronization. On the receiver side, we decode the data streams and extract channel coefficients for digital precoding. The two data streams are decodable, but the EVM is not good. This is mainly due to the interstream interference. In the second phase, we do digital precoding, and here we apply a linear precoding scheme to all the subsequent data streams using the channel coefficients that we extracted as a receiver and which got feedback from the receiver. Then we transmit the newly precoded data frames and report EVM for comparison. As you can observe, the EVM of the decoded frames have improved quite significantly by 5 to 6 dB due to the elimination of the interstream interference. In this project, we have successfully demonstrated our mmWave Fronthaul solutions for an oral network with a cell-free radio access network. Our hybrid 60 GHz MIMO solution serves as an excellent platform for the research and development of next-generation mmWave-based wireless access networks. We plan to explore implementing DSP accelerators on the FPGA and to migrate to an OFDM-based waveform instead of a single carrier waveform. Thank you.